Hello everyone, and thank you for being here today. My name is Blatner. I've had the wonderful pleasure of working in the Bagley lab this past year, and I've been working with a highly innovative new genetic engineering technique known as CRISPR-Cas9. It's actually been termed the molecular scalpel because of how precise it is, so it's very interesting. And this little walkthrough what I'll be going through today. Let's start with background on the key points which I'll be speaking about. I'll speak about how I actually conducted my experiment and then the results of this. Now, a little background on colorectal cancer and why we chose it. It's actually very prevalent in the U.S. Not only is it the second deadliest cancer that they're most commonly diagnosed with, they expect 135,000 new cases this year. There's plenty of people affected by this, and there's a lot of research going into it. It can result due to mutations in a few selected genes, such as APC, TP53, and TPFP. But these mainly control cell growth rate and cell division. So when you start to have mutations in these affected proteins, the cells can start to divide rapidly. Now, colorectal cancer has about 5 stages of growth. Stage 0 is polyps that begins in the mucosal layer and is relatively or easily treatable. Moving to stage 1, this will be the SW480 cells I'll speak about later. Stage 1 colorectal cancer. This is when it starts to breach the mucosa and actually enter the muscle layer, like stage 2. Stage 3 is when it becomes dangerous because now you're entering near the lymph node and blood vessel area. And stage 4 is the SW620 I'll be speaking about later. And this is when you actually start to metastasize throughout the body. As most people know, once it begins to metastasize, it is very difficult. The gene which we'll be targeting in colorectal cancer models is TRIM9L. TRIM9L. So it's first discovered in yeast as TRIM9, and the ortholog is KIA1456 in human models. And we know it's a tumor suppressor gene because in the xenograft model right here to the left, TRIM9L is actually characteristically downregulated in colorectal cancer. And by stage 4 colorectal cancer, it's usually completely gone from the cell. And so we have a control group here, and we have the cell line actually expressing TRIM9L, thanks to research from my lab actually. And they were able to show that the cells that were forced to express TRIM9L had much lower tumor nodule growth rates. And we believe TRIM9L's function is that when they're expressing the cell, and it's upregulated, it upregulates the other gene, the LIN9, which leads to the tumor suppressor level. The genetic engineering technique I've worked with is CRISPR, and it's interesting because we've actually derived this from prokaryotic organisms. And the reason why we've done this is because this is their form of immune system, and that the cell must first survive an initial encounter with a bacteriophage virus. Once it can do that, it can use these Cas proteins, these Cas genes, to insert portions of these viral DNA into their own DNA, known as these PAM spacers in this CRISPR right here. And should it encounter that bacteriophage again in the future, it can actually transcribe this CRISPR array, take these spacers, and now we have what's called cRNA. The cRNA is like a targeting sequence, which can then go and bind to this bacteriophage DNA, and when it's coupled with Cas9 protein right here, it can actually chop up and slice up that DNA, essentially degrading it and rendering it useless. Now, there's 3 forms of CRISPR system. However, we've been focusing on the second one because this is when you use Cas9, and this is when it's use one large protein to actually do the degradation to the DNA. We can adopt this to eukaryotic organisms by actually changing the cRNA to target our specific genome sequence that we like to aim for, and we can couple it with what's called tracer RNA. The tracer RNA is what helps bind the cRNA to the Cas9 protein, and so this is what it can look like. Where you have a large Cas9 protein, you have this what's called guide RNA, and that's the coupling of the cRNA and the tracer RNA. And that'll then bind to your genetic sequence that you like, and it will produce an incision, double-strand break in the gene. Now this is important because what happens is now the cell has to repair the DNA, and it has 2 options in which it can do that. First is non-homologous end-joining repair, or homology-directed repair. Now what we're aiming for is non-homologous end-joining repair, because this is actually error. The cell uses 2 large Artemis proteins to degrade the area around the double-strand break, essentially causing deletions or mutations in this gene. So now the gene is less likely to be transcribed, or proteins that become translated from this gene will actually be defective. So that's one way in which we can gene knockout or silence. And then homology-directed repair is interesting because the cell uses a template strand in the genome to actually guide itself on how to correctly repaired, which makes it much more optimal for gene insertion or gene knockouts. We're looking at silencing TRIM9L, so we're going to aim for the non-homologous end-joining repair path. This is a little animated version of what it could look like. We have a large Cas9 protein, bound to the red single guide RNA in the background and will produce the double-strand break in the DNA. Okay? So what I want to actually accomplish during this study is that first I need to produce my CRISPR construct. So to actually deliver this system into cells, I needed to first inject targeting strands into a plasmid that contains all the necessary components, and then I needed to actually transfect these plasmids into cell culture. I just realized, can everybody hear me in the back, or am I being too quiet?
Oh, it's fine.
All right, good. Let's continue on. All right, so the first step is to actually speak about what cells I'll be using in this experiment. And as I spoke about before, we're looking to use SW480 cells, which are stage 1 colorectal cancer cells. We did this because in colorectal cancer, TRIM9 is characteristically downregulated. However, in this first stage, it's only just begun. So there's still a relatively high expression level of TRIM9L. Whereas by SW620, late stage 4 colorectal cancer, it's almost completely downregulated, so it would be redundant to then excise this gene from the genome. This is the plasmid I've been working with, PX458. As you can see, this large blue arch here is we'll actually be including that large Cas9 protein, so it takes up about half the size. There's a few other characteristic genes in this plasmid I'd like to speak about real quick. So first we have the EGFP gene, and this is GFP bioluminescence. We can use this as a biomarker when we actually transfect our plasmid into mammalian cell culture to determine whether or not our plasmid has actually been uptook by the cells. We have ampicillin resistance gene. This will be important when we're inoculating bacterial cell cultures with our plasmid, because we can use this as a selecting agent to select for only the bacterial cells that have our plasmid. And last, we have this HU6 promoter region, which will be where we're inserting our target strands for the TRIM9L gene. And this is what we'll use to form our guide RNA, our targeting sequence. So how we actually designed that guide RNA, that targeting sequence, is that first we needed to analyze the TRIM9L gene. And in biology, what you want to aim for is the exons in the gene, because the gene is composed of introns and exons. And the exons are the actual encoding region for the functional proteins related to the gene. So what we did is we pulled information from the NCBI FASTA. And what we did is that we started taking chunks from the TRIM9L exons, which there are 4 TRIM9L exons. We ran them through what's called known as the CRISPR design database. What happens here is that you take chunks of sequences from this database and it runs it through and compares it to the rest of the genome. And it gives you a score out of 100 based on how likely the interaction is to be on target. So the farther away from 100, the more off-target interactions you'll have, the more off-target sites and possible cleavages you can have. And in an experiment, when you're trying to control only the editing of TRIM9L, you want to reduce the number of off-target interactions because you want to ensure that you're only editing out TRIM9L. So ideally, we're finding sequences specific to only TRIM9L. We ended up selecting 4 sequences, 2 from the beginning of the exons of TRIM9L and 2 from the end. And we wrote those out for 5' and 3'. Here are the scores that the database gave us. And then we had to synthesize 2 separate strands, so that's what we also had to reverse complement. It was synthesized by IDT, integrated DNA technologies. To actually insert our genetic material into our plasmid, first we must open and it's known as digesting our plasmid. So we have to take our PX458 plasmid and treat it with a restriction enzyme known as BBS1. BBS1 has a GAA-GAC restriction enzyme site. It's interesting because the PX458 plasmid actually has 2 cut sites for BBS1 right next to each other. And it's interesting because what this does, by having 2 cleavage sites, you actually cut out the BBS1 cut site so that it will not recleave itself again in the future. But also by having it in opposite directions, you produce these overhangs that do not match up, so the strand is less likely to reanneal itself before you have the opportunity to actually insert your genetic material. The region in which this insertion is right after the HU6 promoter we spoke about before. To determine whether or not we had actually done this correctly, we ran this through gel electrophoresis, and knowing that the PX458 plasmid is characteristically about 9.3 kilobase pairs long, we can compare it against the ladder to determine that the solution which we have is actually the correct size. So we have our digested plasmid, we have our genetic material. Now we have to actually insert that genetic material. So first we have these what's known as oligonucleotide strands. These oligonucleotide strands become precipitated and need to be treated first. So what we need to do is that DNA has a phosphate backbone. So we need to first add phosphate groups to these 5' ends to continue that phosphate backbone. So we then reanneal, and we did that by running it through a temperature declining temperature ramp. Once we hit this, we now combine our oligonucleotide strands into double-stranded DNA which we now insert into our digestive plasmid. Once we did that, we now had a recombinant vector, which we can, now that we have our ideal vector, we now want multiple copies of our vector to actually transfect into a mammalian cell culture. To do that, was the easiest way in biology, as many people know, is to actually give it to bacterial cells, and bacterial cells will replicate your plasmid along with their plasmid. Now, as I spoke about before, this plasmid has a ampicillin resistance gene out here. And this ampicillin resistance gene is a selective biomarker because we can then use, doesn't come up as well as I hope. There's a lot of, it's a circle, it's a plate, there's a lot of dots, just know that, it worked. It's, so the plate itself has LV ampicillin on it, and the ampicillin will actually select for the bacterial cells that uptake our plasmid, because any cells that don't have our plasmid theoretically would die. So we can then pick colonies from this plate, and by picking colonies from this plate, we can then grow in large LV ampicillin broths to produce greater magnitudes of our plasmid. Now that we have our plasmid, we want to ensure that we have actually made the correct form of recombinant, so we sent our plasmid out for DNA sequencing from the company known as Genewiz. And what we did is that we received these results back of the new recombinant plasmid, and we were able to blast and align our new plasmid to our old plasmid. What this does is that it essentially compares all of the genetic material and gives you a score at the top here by saying how many base pairs line up. Essentially, any shift off from 100% infers that the genetic material has been altered in some way. We can infer that any deviation from 100% in our experiment would mean that we've actually inserted our double-stranded genetic material into it. We can actually ensure that by comparing our oligonucleotides to those different portions of strands, which you can see we have the old sequence and then where our double-stranded DNA actually got inserted into the plasmid. And we ran 4 consecutive trials next to each other, so we have 4 different scores, and each one had a slight deviation, ensuring that each plasmid had to successfully become recombinated with our double-stranded DNA. Now, where we're at now is that we've transfected our SW480 cells with our recombinant plasmid, and we can see that because we can then image our SW40 cells under a microscope and look for that GFP bioluminescence, as I spoke about before. This bioluminescence will show up this green lights in this picture, and that shows all the SW40 cells that actually uptook our plasmid. Now we can analyze the trim9L function of these cells by using molecular techniques such as qPCR or Western to determine whether or not our gene has been transcribed, translated at all, or if any plant proteins have related that produce from the cell. What our next steps are is to evaluate the long-term growth of the SW40 cells. We're looking to examine what happens when you take a stage 1 colorectal cancer cell line and then you remove a tumor suppressor gene. Does it rapidly degenerate into the SW620 level, or does it, what's the growth pattern like? That's what we're looking to evaluate in this experiment. And then we look to then, in the future, possibly transfect our plasmid into similar cell lines, other cancer cell lines, to evaluate what happens when you remove a tumor suppressor gene from those lines. And of course, I'd like to thank everyone I've worked with this entire year. They've been more than helpful. They really carried me through this, and I cannot thank them enough for all this. So I think they deserve a round of applause themselves, but that is the end of my presentation. Thank you. Yeah, that's okay.
Are you trying for point mutations or big deletions? Right.
Ideally, large deletions, because that would remove about any chance of successful still transcription of the trim9L gene. So by taking large chunks out, it's much less likely to, I know it's not really trying to go to right now. There we go. By taking large chunks out, then it's much less likely for any kind of functional protein to be transcribed and translated from this.
Do you have to check your mammalian cell line? I forgot what cell line it was.
Yes, SW40 colorectal cancer cell lines.
You sequence those or run a
Yeah, we can do that to also determine whether or not our trim9L has been deleted from the gene. More questions, please. I'm prepared for plenty of things.
Can you go to your sequence identity? I was a little confused with that.
Oh, okay.
Real quick.
So
when you did the sequencing,
So here?
no, the sequencing that you actually did.
forward.
Keep going. Where you identify the original sequence and the
Oh, yes. Okay. So
that.
So
So what you're showing here is the old sequence is the same as the oligonucleotides. So you got the plasmid there, and then you get the recombinant. But it looks like if you look at the yellow and the green region, aren't they the same?
well, there's a slight shift in the difference, you can see there's thymines where there might be cytosines, adenosines where there might be guanines.
Is that the insertion site where you put the sequence in?
Well, yes. So you can actually match this entire strand up to this portion right here. How I want to highlight the differentiated portion.
No, but is that the sequence of base pairs that you inserted? Is that where the BSL3 sites were, the BSL1?
I believe so. The restriction enzymes are actually designed to cut out their restriction enzyme cut site.
So this is what I'm not getting, is why does the old sequence still retain all that sequence from the recombinant one that you made too? You're blasting the two, you're doing a sequence
Yes.
alignment of the original and a sequence alignment of what you've inserted,
Yes.
but I don't see any difference.
Between these two strands.
Yeah, besides those two base pairs that could just be misreads or whatever.
It could be misreads. I believe there's a good standard. There's a few. There's a different. I mean, I'm unsure of how to what the actual site that got removed from. And I can
Methodically walk them through it.
So there was the PBS1 restriction enzyme site in which we then use a cutout and then insert our oligonucleotide plasmid. So there's a portion of that plasmid now missing because those PBS1 cut sites have been removed by themselves cleaving themselves out, essentially due to their opposing directions, like leaving these overhangs. But we have our oligonucleotide sequence here, which then matches up to the new oligonucleotide sequence here, which is slightly different than the one up here.
Okay. I guess it's just the way it's represented because you got an alignment. If it's a mismatch, it shouldn't.
Okay.
It should not. It should be a gap there.
Okay. Yeah, I'm sorry about that.
That's all right. No, I just wanted to make sure there was an insertion there.
Okay. Any other questions?
Okay, now let's thank our speakers.